Hello everyone. So in this video we are going to discuss about the region of convergence for the Laplace transform. We have seen that in our previous video how to calculate the Laplace transform, and I've already given an intuition of what is region of convergence. Region of convergence we will refer to as ROC in further descriptions, and we will see the importance of region of convergence. We have already seen that like for few of the signals the algebraic expression for the Laplace transform is same. So algebraic expression was same, but ROC was different, and this different ROC is basically define that signal in a better form. So we need both of this form, that is algebraic expression in ROC, to describe the Laplace transform. And if ROC is important, we have to know some of the properties of ROC in order to understand the Laplace transform in a better manner. So in this video we will discuss about some of the properties of ROCs which will help you to find the Laplace transform of some signals in an easier manner, and you will understand more about the region of convergence and stability and instability of signal and system. So we'll start with first of the properties. So what will be the first property of ROC? The first property of ROC states that the ROC of x of s consists of strips parallel to the j omega axis in the s plane. So I'll discuss it in details. So we have some of the keywords here. First we are telling that the region of convergence of x of s, then we are telling that strips parallel to the j omega axis in the s plane. So I'll describe one by one. So we have a signal xt, and we are telling that its Fourier transform is x of s, and we are telling that the ROC of x of s consists of strips parallel to the j omega axis. So we have already explained what is the s plane. So basically s refers to a value which is containing of sigma plus j omega, and sigma here is your real part and j omega is your imaginary part. So s plane consists of two axes in which real part is denoted by sigma and the imaginary part is denoted by j omega. So this is the j omega axis. We can also say it as an imaginary axis. So now let's understand this property with some of the descriptions. So we are telling that Laplace transform is defined by the formula xt e raised to the power minus st dt, and that has to be convergent in order to define that Laplace transform. We have already seen an alternate way of representing Laplace transform. So what is the alternate way? So alternatively what we have said that Laplace transform is Fourier transform of the signal xt e raised to the power minus sigma t. So Fourier transform of this signal is basically your Laplace transform. We have already seen in this previous video. You can refer to the previous video to understand this form. So now from this intuition what we can say that ROC of xs consists of those value of s is equals to g sigma plus j omega for which the Fourier transform of this function will converge. So especially we want those value of s. So s is basically sigma plus j omega, and we want those s value for which this expression converges. Then only the Laplace transform will be defined. So how we can write it in the mathematical form? We can write it as minus infinity to infinity mod of xt multiplied with e raised to the power sigma t dt should be less than infinity. So if this is integrable, then we can say that Laplace transform is defined, and those values of s will be in the ROC of xs. So that will be in ROC of x of s. So this is basically the alternate way of understanding the ROC. And now here you can see that in the whole expression what is the variable? Variable is your sigma value. So sigma values. So as we have already drawn the s plane, so if we will take different values of sigma, what will be those values? Suppose we have taken a sigma value of some sigma 1, some sigma 2, similarly sigma 3. So all these values basically are parallel to the j omega axis. So this is the imaginary axis. So they are parallel to your j omega axis. So this property basically specifies that the ROC of x of s consists of strips parallel to the j omega axis in the s plane. So we can understand by this small derivation, you can say. Now we'll move on to the next property. So what does the next property state? So property number 2 states that for rational Laplace transform, so for rational Laplace transform, the ROC does not contain any pole. The ROC does not contain any pole. So here what we have to understand, what is the pole, and we have to understand what is a rational Laplace transform. So rational Laplace transform is basically in form of P by Q, and Q cannot be 0. So basically the basic definition, so suppose we have a Laplace transform of the form 1 upon s plus 1 into s plus 2. So this is kind of a rational transform, and we have pole at s is equals to minus 1 and s is equals to minus 2. So at these values the denominator became 0. So if we'll have pole, we'll get a value of xs to be infinite. So suppose, and you can see, suppose we put s is equals to minus 1, what we'll get? We'll get the x of s as an infinite value. So basically x of s become infinite at poles, and if this is infinite, the Laplace transform integral does not converge at the pole. So we will not get the convergent Laplace transform at pole. That's why we are saying that for rational Laplace transform, the ROC does not contain any pole. So we have to exclude that pole, because at that pole the Laplace transform does not convergent and we don't have any value, so we will get x of s as infinite values. So this is the property number 2. So we'll move on to the next property. Next property states that if x of t is finite duration and is absolutely integrable, then the ROC is the entire S plane. So this property is very important, you have to understand it. So what we are saying that if x of t, that is if signal is finite duration and is absolutely integrable and is then the ROC is entire S plane. So let's first understand what does we mean by finite duration, then we already know what is absolutely integrable, and then we'll see how the ROC will become the entire S plane. So absolutely integrable function is basically you have to integrate it to minus infinity to infinity, and you will get some finite value that says it's absolutely integrable. Finite duration is basically the signal is having values between two values. Suppose we have t1 and t2, and the signal is defined in between this t1 and t2 in some arbitrary manner, and apart from this the signal is having a 0 value, so it is not having any other value. So this signal is defined for some finite duration. That's why we are saying that xt is a finite duration signal. And as per the definition of absolute integral, what we'll say xt, basically mod dt, that from t1 to t2, because it is a finite duration signal, should be less than infinite. So this is saying that the signal is finite duration and absolutely integrable. So it is defined from t1 to t2, and the mod integral is less than infinite. Now from the definition, if s is equals to sigma plus j omega to be in ROC, so if we want this value to be in ROC, what we want xt e raised to the power minus sigma t to be absolutely integrable. We have seen that this is basically The Fourier transform, this is Laplace transform, and if this is absolutely integrable, our Laplace transform is defined. So if we want this value of s is equals to sigma plus j omega to be in ROC, this should be absolutely integrable. And now for this, how we can write? So we have an integral t1 to t2 mod of xt e raised to the power minus sigma t dt should be less than infinite. So if we put sigma is equals to 0, what this it means, we'll get this form back. So suppose we put sigma is equals to 0, this value become 1, so we'll directly get t1 to t2 mod of xt dt integral, which should be less than infinite. So s will be in ROC. So this is pretty much clear. If sigma is equals to 0, then s is in ROC. Now we'll take a value of sigma which is greater than 0. So 0 we have already seen that is in ROC. Now we'll take sigma which is greater than 0. So the maximum value of e raised to the power sigma t over the interval on which xt is non-zero is e raised to the power minus sigma t1. So we have taken that limit from t1 to t2, and if we want the maximum value of sigma t, so we have e raised to the power minus sigma t, and what will be its maximum value? Because it's a decaying value, so for e raised to the power minus sigma t1, it will get the maximum value. So the max of this value will be e raised to the power minus sigma t1. So how we can understand it as, so we have t1 to t2 mod of xt e raised to the power minus sigma t dt, and that should be less than what? E raised to the power minus sigma t1 to t2 integral mod of xt dt. We have split this value because this is the maximum value it can attain. So we have said that this maximum value multiplied with this integral, and that is maximum, so our integral is less than that of that value. And as we have seen that this is bounded signal, so we have this as bounded. We have already seen that this is absolutely integrable. So region of real part of s greater than 0 must also be in ROC. So we have taken sigma greater than 0, then we have seen that the maximum value of this will be attained by e raised to the power minus sigma t1, and for our integral all the value will be less than this value, and this itself is bounded, so this integral will also be bounded if sigma is greater than 0. So we can say that real part of s which is greater than 0 must also be in the ROC. Similarly, we will take the value sigma which is less than 0, and we will do the same analogy. So what we will get? We will get t1 to t2 x of t mod e raised to the power minus sigma t dt, and this value will be less than what? If you can guess, e raised to the power minus sigma t2. So now we have to take sigma t2 because it's the sigma value is less than 0, so we will take the greater value. So if range is from t1 to t2, we have to take e raised to the power minus sigma t2. The max of this will be e raised to the power minus sigma t2, and again this integral will be t1 to t2 mod of xt dt, and again we have said that this is bounded. So we have real part of s less than 0 must be in ROC. So we have real part of s less than in ROC, we have real part of s greater than ROC, and real part of s0 is in ROC. So what we will get? We will get the ROC includes entire s plane. So this is the property. So if we have a finite duration signal, so we can say that the ROC includes entire s plane. So we can understand it with some example also. Suppose we have taken a signal x of t, which is a finite duration signal, and we define it as e raised to the power minus at for a value 0 t to capital T, it is 0 otherwise. So you can directly say that this is finite duration signal because it is defined for two values in a range which is varying from 0 to capital T, and the signal is defined only in that range, otherwise it is 0. So let's take the Fourier transform. So x of s will be equal to 0 to t e raised to the power minus at e raised to the power minus st dt from the formula. What we'll get? We'll get 1 upon s plus a 1 minus e raised to the power minus s plus a t dt. And as it is finite duration, we can say that the ROC will contain entire S plane directly. Some of you will get confused by the form of this Fourier transform because you can see that there is a pole also. So you can argue that for s is equals to minus a, this point cannot be included in ROC, and you cannot say that ROC is the entire S plane. But if you carefully see this form, if you will put s is equals to minus a, then both the numerator and denominator will be equal to 0, and we have to apply L'Hopital's rules. So suppose what we'll say, we'll say limit of x, so basically s tending to minus a, x of s should be equal to limit s tending to minus a. So what we'll do, we'll have to take derivative on both numerator and denominator. So we'll take 1 minus e raised to the power s plus at divided by d of ds of s plus a. So this will be equal to limit x s tending to minus a t into e raised to the power minus at e raised to the power minus st. And so what we will get, we will get x of minus a as capital T. So it is defined at minus a also. So it's not the form only, you don't have to basically confuse with the form. So if you are directly seeing that rational form, and you cannot directly say that it is having some pole at that value. So we have to check the numerator and denominator also. If both is getting 0, then that is not in a rational form, and we have seen that for s is equals to minus a, it is defined as t. So for this finite duration signal, the ROC contains the entire S plane. Now we will move on to our fourth property. So fourth property is defined as if xt is right sided. So if our signal xt is right sided, and if line real part of s is equals to sigma naught. So we have taken a specific value of sigma which is equal to sigma naught. So if the line real part of s is equals to sigma naught is in ROC, so we are telling that this value is in ROC, then all values of s for which real part of s is greater than sigma naught will be in ROC. So this is quite intuitive, you can directly understand. We'll also see some mathematical expression to understand it better. So what we are saying, if xt is right sided, I'll explain shortly what is right sided, and if line real part of s is equals to sigma naught is in ROC, then all values of s for which real part of s greater than sigma naught will be in ROC. So how we can understand it? So first we'll understand what is a right sided signal. So right sided signal is basically just xt which is taking 0 value prior to some finite time t1. So for some prior value of t1, so suppose we have taken t1, so prior to that this signal will take xt is equals to 0. So xt is equals to 0 prior to some finite time t1. So how we can understand it graphically? So suppose we have some arbitrary signal, so this is your time axis. So we have taken a time t1, and before that the signal is 0, and for value greater than that t1 value it is defined, and it will move on to the infinite value. So that is the right sided signal. Now what we are saying, we are saying that we have taken sigma at a specific value sigma naught. and we are telling that this is in ROC. That means that Laplace transform converges for this value. So if we are taking sigma is equals to sigma naught, the Laplace transform will converge. This is already defined. So from the expression, what we can say that expression of minus infinity to infinity mod of xt e raised to the power minus sigma naught t dt is less than infinite, because it is defined at sigma is equals to sigma naught. Now because it's right sided, what we can write? We can write it as t1 to infinite xt e raised to the power minus sigma naught t dt should be less than infinite. Now what we'll say, we'll take a value sigma 1 which is greater than this sigma naught. So now we have to check for t1 infinite xt mod t e raised to the power minus sigma 1 t dt. If it is less than infinite, then we can say that this value is also is in the ROC. So just see the form e raised to the power minus sigma naught t dt. So this is having value sigma naught and this is in ROC. Now we are saying that we are taking a value which is greater than this sigma naught, that is sigma 1 t into dt. This sigma 1 is greater than sigma naught. So what we can say, because of the negative exponential, it will decay faster as compared to this. And if this is in ROC, then this must definitely be in the ROC, because it is decaying faster than the previous one. So that's why we are saying that real part of S which is greater than sigma naught will be in ROC. Now we'll move on to the next property, and the next two properties are quite analogous to this property. There is some slight changes only. So what is the fifth property? Fifth property says that if xt is left sided, so now we have just changed the scenario. We are saying that if xt is left sided, and again if the line real part of S is equals to sigma naught is in ROC, then all values of S for which real part of S is less than sigma naught will also be in ROC. This is quite intuitive. Again, if we'll take a value for this S which is less than that of sigma naught, because of left sided. So what is left sided? For left sided, the signal will have an upper limit of suppose some value t1, and for that value greater than t1 the signal is 0, and for all other values it is defined. So this is your left sided signal. And again, if real part of S is equals to sigma naught is in ROC, so if we'll take any value which is less than this sigma naught, the exponent e raised to the power minus sigma naught t will decay faster. Again the same analogy, there is no difference in it. So again we can say that real part of S which is less than sigma naught will also be in ROC. And again the next property is again the analogous, or we can say the combination of these two properties. So the sixth property is combination of again the fourth and fifth property. What it says that if xt is two-sided, and if the line real part of S is equals to sigma naught is in ROC, then the ROC will consist of a strip in the S plane. That include the real part of S is equals to sigma naught. So how to understand a two-sided signal? So in this we don't have any limits. So here use your xt. Suppose I just wanted to depict it graphically. So this is your signal. So there is no boundation at both of the sides. So that's why we are saying it as two-sided signal. So in order to understand it, we can split this signal in two forms. Suppose we pick a value t naught, and we can say that this signal is combination of these two signals. So we have a signal which is right sided at t naught, and there is another signal which is left sided. So this is left sided. So we have two signal, one is right sided and another one is left sided, and you can see that these two sided signal can be interpreted as a combination of right sided and the left sided. So we have already seen the properties of ROC for right sided and left sided. So just we'll draw up the ROC. So for the right sided, what we have said that for any value, suppose we have taken some sigma r, all the values which is greater than this value will be in the ROC. And for left sided, what we have seen that we have, suppose we have some sigma L, so all the values which is less than this value will be in the ROC. So if we are combining these two, what we can say that we have the ROC will be in between these two values. So we have sigma r, we have sigma L, and our ROC will be the strip in between these two values. So that is basically your definition. By definition, what we are saying that if xt is two-sided and if the line real part of S is equals to sigma naught is in ROC, then the ROC will consist of a strip in the S plane that include the real part of S is equals to sigma naught. So we have this strip between sigma r and sigma L, and it will consist the value sigma naught. So this is the way to understand the two-sided signal. So let's understand the two-sided signal with one example also to get the better intuition out of it. So suppose we have a two-sided signal which is defined as xt is equals to e raised to the power minus b mod t. So you can have the graphical intuition of this function as, so we have your function, it will take a value of 1 for t is equals to 0, and it will decay on both of this side. So this is your t axis, and we are drawing e raised to the power minus b mod of t, and this will be for b greater than 0. And if we'll take b less than 0, then what will be the value? So for b less than 0, it will be an increasing value. So this is your e raised to the power minus b mod t, and this is your time axis. So this is the graphical intuition of both of this curve for b greater than 0 and b less than 0. So because it is two-sided signal, we will divide into sum of right side and left side. So we will divide the signal in terms of right side and left side. So we have one function will be as e raised to the power minus bt ut, because we are taking the positive values t greater than 0. So this will be your first part, and this will be your the second part. So the first part is represented as e raised to the power minus b ut, and the other part will be represented as e raised to the power plus bt u of minus t. So these are the two signals. One is your right sided, other one is your left sided, and we are saying that this is the combination will make your original signal x of t. So from the Fourier transform property, we know that the Fourier transform of this signal will be represented by 1 upon s plus b. The only difference, so this will be having Fourier transform of minus 1 upon s minus b. Now the algebraic expression is done. Now we have to define the region of convergence. For this, real part of s should be greater than minus b, and for this, real part of s should be less than plus b. So this form you can directly use from your Laplace transform formula, and from here you can say that for the right hand side signal, the real part of s is greater than minus b, and for the left side signal we have real part of s less than plus b. So if we'll see the combination of these two, what will be the combination? So we have xt as the combination of these two, so we can write e raised to the power b of mod t will have Laplace transform of combination of these two. So we have 1 upon s plus b minus 1 upon s minus b, that will be equal to minus 2b s square minus b square. And the combination of these two Laplace transform will be, we have a strip between these two values. So this is your minus b, this is your plus b, and we'll have the strip between these two lines. So what we can say, that real part of s will lie between minus b to b. So this is your region of convergence, and this is your algebraic form of this expression. Now we'll discuss two of the simpler property, or last two property. So seventh property states that if Laplace transform, xs of xt signal is rational, then ROC is bounded by poles or extend to infinity. This is quite intuitive, so it will extend to infinity. And we have already said that the pole will not be contained in that ROC. We have seen that at pole what will happen, it will go to infinite. So poles of x of s are not contained in ROC. So we are telling that if Laplace transform xs of xt is rational, the ROC is bounded by poles or extend to infinity. So if we have 2-3 poles, so either it can go from one pole to infinite, or it can be bounded within the poles, and we have to explicitly state that the poles are not contained in that ROC, because at poles we will get the non-convergent form of the Laplace transform. So the values is not defined. So the last property is your property number 8, and this is quite important. What it states that if the Laplace transform, so if the Laplace transform x of s of xt is rational, then xt is right sided, then if we are saying that then if xt is right sided, the ROC in the region in the S plane to the right side of the rightmost pole. So we have the ROC is the region in the S plane to the right of rightmost pole, and vice versa. If this is left sided, then we can say that the ROC is the region in the S plane to the left of the leftmost pole. How to understand this? Suppose we have two poles, and if you are saying that the signal is your right sided, so the region of convergence will be the right of the rightmost pole. So rightmost pole will be this, so the region of convergence will be right to the rightmost pole. And if the signal is your left sided, so if you have two poles, so the region of convergence will be left to the leftmost pole. So this is the form to understand that if the Laplace transform of excess of xt is rational, then if xt is right sided or left sided, the ROC is the region in the S plane to the right of the rightmost pole or leftmost pole, depending upon the signal. So this is the way to understand this property. So this is it. This describes your properties of region of convergence, and that is very essential to define the Laplace transform of various signal, and that we will derive in your further videos.